I'm giving the TA for Ofer Zaitouni's course about branching random walks. And so today what are we going to do? I'm going to do first, I'm going to recall essentially Cramer's theorem. So from large deviations. I'm going to do 2 exercises from the lecture notes. And if time permits, I'm going to define general branching random walks. So BRW means branching random walk. And I'm going to introduce the so-called spine representation of branching random walks. So with general, I mean you have general reproduction laws, and so general offspring distribution. Okay, so let's start with Cramer's theorem. So the setting is we have a sequence of IID random variables, and we suppose for simplicity that the Laplace transform of these random variables is finite for all lambda. And we also suppose that the expectation is 0 and that the variance is positive. So no deterministic case. Okay, and then we define. Oh, so can you read it? The screen is on there. Okay, good. So now we define the log Laplace transform, capital lambda is so the log of the Laplace transform. And so first of all, I'll state some properties, so which are easily to check. Okay, so first of all, if you take the limit as lambda goes to plus infinity of the log Laplace transform divided by lambda, so this converges to the essential supremum of x1. So the essential supremum, this is the infimum over all x, such that the probability that x1 is greater than x is 0. And because of our conditions here, we know that this is strictly positive. And if you take the limit as lambda goes to minus infinity, then this converges to the essential infimum, which is strictly negative. Okay, so typically lambda looks like this. So there are some other properties here. So we will show that, oh no, you know this, that lambda is a smooth function, is C infinity. And moreover, so because of this hypothesis, the derivative of lambda in 0 is 0. Okay, so this is, well, maybe I'll write this down. So the derivative of lambda in 0. So this is the derivative of the Laplace transform in 0. So it's the expectation of x1 e to the lambda x1 divided by the Laplace transform. So take it for lambda equals 0. And this is the expectation divided by 1, so this is 0. And moreover, if you take the second derivative, then you see that So you get the second moment, and by the hypothesis that the variance is strictly positive, we have that also lambda is strictly convex. Okay, I can't put this. Okay, so let's take two examples. If x is the normal distribution, then what's lambda? Quickly. Thanks. So lambda is lambda squared over 2. And if we take the Bernoulli distribution, so with mean p, for example, then so we can just write it down. It's the logarithm of p e to the lambda plus 1 minus p. Okay. Okay, so now from capital lambda, we're going to define the rate function or the Legendre transform of lambda. So that's the function Ix, so which is defined as the supremum of all lambda of lambda x minus capital lambda. Okay, so we're going to do some, yes, some question? No. Okay, some exercises we're going to do. So show that I0 is 0, that Ix is finite on essential infimum of x1, essential supremum of x1. Ix is infinite on the minus infinity essential infimum of x1, and to the right of the essential supremum. Furthermore, the rate function is smooth, or at least on this interval. And it's strictly convex. And its derivative in 0 is 0 as well. Okay, so these are some warm-up exercises. Okay, so first of all, well, I0 is 0. Well, this is just by the definition. So if we plug in x equals 0 here, we have that this is just, so the supremum of minus the log Laplace transform. And this is 0. So, well, maybe I just draw a picture of the rate function. So we have here the essential supremum, say, here the essential infimum, and we have this kind of picture, and here it's infinity. And what happens at these points is a priori known. Okay, so now if we take some x in this open interval. So then we know by these facts here that lambda x minus the log Laplace transform as the lambda goes to plus infinity or minus infinity, this goes to minus infinity. So the rate function must be finite. If we take x which is greater than the essential supremum, so then again, so by these facts we know that lambda x minus the log Laplace transform goes to plus infinity as lambda goes to plus infinity. And so this says that the rate function is infinite. And, well, in the case of the essential infimum, then it's the same. Okay, so now let us show that the function is smooth and strictly convex. Any questions so far? Okay, so how many of you have seen this several times and are perfectly fine with that? Okay, how many of you have seen this once but don't really recall? And so the rest have never seen this? Okay. Or did I leave out some answer? How many of you have seen this twice and don't recall that well? All right, so we're gonna study strictly convexity and smoothness. And for this and something, well, which we're gonna use more often, we're gonna look at the lambda which maximizes this quantity here. So we want to get a relationship between I and lambda. Okay, so, well, we know by what we just wrote here that this supremum is actually attained, so it's a maximum. So there exists some, so for all x, there exists some lambda x with Ix is lambda x minus the log Laplace transform. And, well, so we want to find this lambda. And, well, this is just basic analysis. The derivative of this term has to be 0, of course, in this lambda. So lambda, so when we derive this term by lambda, we get x is lambda prime x of capital lambda x. Sorry, lambda prime. Sorry, we derive this term by lambda, so it's just this. Okay, so this means that lambda x is simply the inverse of the derivative of the log Laplace transform. And why is this inverse well defined? Well, because the log Laplace transform is strictly convex. And so its derivative is increasing. And so it has a well-defined inverse. And now lambda x is simply this inverse here. Okay, so furthermore, lambda is, so the log Laplace transform is strictly convex. So it means that its second derivative is not 0 at some point, and it's C infinity. And so this yields that lambda itself is C infinity. Okay, now furthermore, if we plug this in here and derive, so calculate the derivative of the rate function, so then we see it's lambda prime x plus lambda x minus lambda prime x, and the derivative of the log Laplace transform. And so this one here is simply x. So these terms here cancel, and we see that the derivative of the rate function is simply lambda x. Okay, and since now since lambda is strictly increasing, because it's simply the inverse of a strictly increasing function, we see that the rate function itself is strictly convex, and moreover, we also get that it's C infinity. So I is strictly convex, and C infinity. Right, and well, moreover, the derivative of I, so I'll just put this down here, in 0 is now simply lambda 0, which is 0. Okay, so these were some basic facts about this rate function, and now I'm going to recall Cramer's theorem and prove it. So where this rate function plays an essential role. So we define the random walk as n, which is simply the sum of the first n variables. And now Cramer's theorem says that the probability that Sn is greater or equal to xn, so x here is some positive number which is less than the essential supremum. So this probability here behaves like e to the minus, behaves like minus, so the logarithm divided by 1 over n of this probability converges to minus the rate function in x. Okay, so the limit as n goes to infinity of 1 over n, the logarithm converges to the rate function. Okay, so this is Cramer's theorem. So of course, this statement can be rendered much more detailed, but well, for the first approximation in the logarithmic scale, this is the first approximation. Okay, so how do we prove it? Well, the upper bound is quite simple. Well, it depends on a good trick, which is called Chernov's bound. Okay, so by Markov's inequality, we simply bound this probability by the expectation of e to the lambda Sn minus xn. Okay, this is simply Markov's inequality. If Sn is greater or equal to xn, then this term here is greater or equal to 1. Okay? So this is true for any lambda. And now, so this is just the Laplace transform. So this is the exponential of n times the log Laplace transform minus lambda x. Okay, so this was for any lambda. So now, if we take the infimum over this, then this gives us immediately the upper bound. Yeah, so we just take the infimum over lambda. Okay, so this is called Chernov's bound. And the lower bound now will be proved with a technique which we're going to use later as well, in order to study the spine representation I already hinted at, which is called tilting. So, which means that we will change measure with respect. So we will use an exponential weight in order to change the measure of the law of x1. All right, so first of all, let's take some lambda, and then we define, so this tilted measure, so we're going to denote it by q, and the original measure, well, I didn't write it, but we're going to denote it by p. And so now we define, so the Radon-Nikodym derivative of q with respect to p on the filtration, or on the sigma algebra of the first n steps. Okay? So we set it to be simply e to the lambda Sn minus n capital lambda. Okay, so why does this define a probability measure? This you can simply prove it by recurrence. So for the first step, this is simply by the definition of the Laplace transform, and then just define it by recurrence. So you see that so the expectation of this with respect to p is 1, and therefore q is still a probability measure. So q is probability measure. Okay, I should say maybe, so here we defined q on these sigma algebras. So if you call this, for example, Fn, and we can define q as well on the limit of Fn, so on F infinity by Kolmogorov's extension theorem. So although here we define only a measure on this sigma algebra, we can extend it by Kolmogorov's extension theorem. All right. Okay, so now what's the expectation of x1 under this measure q? So in order to calculate this, we use here this density. So this is the expectation with respect to p. So in what follows, if I take expectation with respect to q, I'll always put it down here. If I take expectation with respect to p, I just leave it empty. So this is the expectation of x1, and here this term, e to the lambda x1 minus the log Laplace transform. Okay, so how do we calculate it? We did it before already. We simply derive by lambda. Okay, so this term here, we can also take it outside. And now we just take the derivative of this here by lambda. So the derivative by lambda of, and this is here e to the log Laplace transform, e to the minus the log Laplace transform. And calculating this derivative, you see that this is simply the derivative of the log Laplace transform. Okay, and if we choose here as lambda x as we've just defined it, then we see that this is just x. We calculated this before. So in choosing here this particular lambda, we start with a measure which has expectation 0, and we end up with a measure which has expectation. And now this will allow us to prove Primacy theorem. So we want to bound from above the probability that Sn is greater or equal to Xn. From below, sorry. So now we do this change of measure here, but the other way around. So first, here we let appear this term e to the lambda Sn minus n, the log Laplace transform, and we take it away artificially. Here xn. And here's a minus. Okay, now this term here will change the measure. So this is the expectation with respect to the measure q of the indicator that Sn greater or equal to Xn. And we have this term here. And this term here is deterministic, so we put it out. Okay, so this seems to lead to nowhere because, well, we have a lower bound on Sn, but this quantity here is decreasing in Sn, and we want to bound it from below. So what we're going to do is we say this here is greater or equal to the quantity if, in addition, we cut off Sn. So we say that Sn is greater or equal to Xn, but smaller than x plus epsilon n. And now if we do this, then this term here is of course greater than e to the minus lambda x plus epsilon n. And we still have here n, the log Laplace transform. Okay, so this here is true for any positive epsilon. Okay, now this quantity here is then the probability under Q that Sn is between Xn and x plus epsilon n. And now we just simply use the fact that Sn is a random walk with expectation x. And we can use then the central limit theorem that this quantity here converges to 1/2 as n goes to infinity. Okay, and so here I didn't say it, but here I choose, of course, lambda to be lambda x. Okay? And if I choose lambda to be lambda x, then this quantity here is e to the minus the rate function and minus lambda epsilon n. Okay, sorry, here is an n. Okay, so now we just take the logarithms of both quantities, divide by n, and then let first n go to infinity and then epsilon go to 0, and we get what we want. Okay, so first let n go to infinity, then epsilon go to 0, and this finishes the proof. Okay, do you have any questions about this? No? All right. So before I'll go on to these exercises, just the two examples, say the basic examples. For the Gaussian distribution, so we saw that the log Laplace transform is lambda squared over 2. And what's the rate function? Did anybody calculate or know it by heart? Sorry?
X squared.
Thanks. So it's exactly the same. And for Bernoulli variable, so either you calculate it by hand or you use Sanoff's theorem. And Sanoff's theorem tells you that the rate. Do you see this here? Yeah. Well. So Sanoff's theorem says that the rate function is well, in this case it's, well, in general it's so if you have a law which is concentrated on a finite number of points, then it's the minimum overall probability laws which have mean x. So here it's the minimum, so overall mu, so in a probability law on 0, 1, such that so the mean of mu is x, and the minimum of what? Of the conditional entropy of here this Bernoulli variable with respect to this law mu. And this, you get it, is x log x over p plus 1 minus x log 1 minus x over 1 minus p. So this looks something like this. So here we have 0, we have 1. Say here we have p. So the rate function is, of course, 0 at p. And then we will have something like this here, with the derivative here being infinite. Okay. And here it's plus infinity. Okay, so this is the rate function for the Bernoulli distribution. Yes? Okay, so that's the minimum of all probabilities on 0, 1. So these are the minimum of all Bernoulli laws on 0, 1 with mean, so mu of 1 is x. Okay, so there is only one. It's just the Bernoulli with mean x. So if you have more than one atoms, then you have a family of probabilities that satisfy this. But in our case, it's only one. It's Bernoulli x. And then we get the conditional entropy of the Bernoulli p with respect to this law mu. And this is this. Okay, so that was Cramer's theorem, and now I'll continue with some exercises. So two exercises that author was hinting at today during the lecture. So the first one is, suppose we have two random variables, x and y, IID, and suppose that we know that the expectation of so the absolute value of the difference of both is bounded. Okay, so now show that the expectation of x minus the expectation of x, so absolute value of this is then also bounded, so from above by this c. Okay, this we will see, this is an exercise in conditional expectation. So we will actually show that this quantity here is strictly smaller than this one. Okay, so if we calculate this, then we use the Tower property of conditional expectation. So we condition here with respect to x and take the expectation of this. Okay, so this is the Tower property of conditional expectation. Okay, so now anybody's got an idea how we can proceed? Again? Jensen, exactly. So now we use Jensen's inequality to take here this absolute value outside of the expectation. Okay, Jensen, well, the conditional Jensen inequality. Sorry. Up. Okay, so this one here is for the conditioning, and these ones here are for the absolute value. Maybe I'll make this one here slightly smaller. Okay, so now we use the fact that y is independent of x, which will give simply here that the expectation of y conditioned on x is simply the expectation of y. And since both have the same law, this is also the expectation of x. Okay.
won't be absolute values. Show that expectation of x minus absolute value of expectation of x.
Yeah, you have one more.
Right, thanks. There's one expectation. That's too much. Thanks.
I meant in the statement. Show that the expectation.
In the statement up there, well, this one here is the E with the double bar. Okay. Right. Okay. So that was the first exercise. And the second exercise is the following. So take a sequence AN, which is positive, sequence of positive numbers, and suppose that the Cesaro sum of these numbers converges to some constant. Sorry, AK. Okay, so 1 over n times the sum of the AK from k, for k from 1 to n. And now we want to show that for every delta, every positive delta, there exists a constant depending on delta, and a sequence nk with nk over k. So the lim sup of nk over k, we want it to be at most 1 plus delta, so we want to have a sequence which is as dense as we want. And we want that A and K is less than this constant K here for all K. Okay, so to do this, we will construct such a sequence. Well, I can erase this anyway, I think. Can I erase this? Yeah. Okay, so this was in the proof of the tightness of the maximum of the branching random walk. Okay, so here the AN were the expectation of Mn plus 1 minus the expectation of Mn. Okay, and we wanted to show that, so we knew that the expectation of Mn over n converged to some constant, and we wanted to prove tightness of the maximum over such a subsequence. And well, this gives this statement here. Okay? Okay, so fix delta, and we're gonna suppose that it is less than 1. And now we define the following sequence. We start with 1, And now we define nk plus 1 to be the first number after nk such that an is less than or equal to 2c over delta. Okay. Okay, so first of all, this number exists because otherwise the sum over the an up to over the ak up to n would be greater or equal to this constant here times n, and this is not possible because we know that the Cesaro limit converges to some constant c, which is strictly less than this one. Okay, so this is finite. And furthermore, if we set capital Nk to be the number of numbers less than k, which are not in this subsequence. Okay, so we want to show that this sequence is indeed dense. Okay, so we want to count the first, so the numbers up to k which are not part of this subsequence. Okay, so how large can this be? Okay, simply if we sum over all of these numbers, so all of these numbers here in this sequence don't satisfy this. So if we sum over them, so if we take the sum over a n ani for I from 1 to nk, then this must be greater or equal to nk times this constant here. But since the a's are positive, this was a hypothesis we made, so this here is less than or equal to the sum over I from 1 to k. And we know that this one here divided by k has a lim sup which is so converges, and therefore here the lim sup of this one of nk over k. So this one here divided by k converges to c, and therefore the lim sup of nk over k is less than or equal to delta half. Okay, so we kind of constructed the subsequence by looking at those that we don't want to be in the subsequence. Well, no, we didn't construct it like this. Okay, so now we know that the number of numbers not in our subsequence, so here we have an upper bound, and this gives us that the limit of now the numbers in our subsequence is greater or equal to 1 minus delta half k, so up to k. Okay, so this means now that if we take the 1 minus delta half kth number, so take the ceiling, for example, so that this makes sense. So then this number divided by k has a lim sup then, which is less than or equal to 1. Right? And now we simply multiply by 1 over delta half, or we divide by 1 minus delta half to get that the lim sup of nk over k is less than or equal to 1 minus delta half. So 1 over 1 minus delta half. And this is because delta is less than 1, this is less than or equal to 1 plus delta. Okay. So this is quite a quite nice idea to take here the subsequence. All right, so I still got, say, 6.5 minutes to introduce the general branching random walk. Okay, so maybe the most important thing is to give you a good reference. So, third, general branching random walk and spine representation. So I give you the reference of the first paper where this spine representation was introduced in this form for branching random walk. So it existed way before in the literature. So those of you who know super processes, Evans' immortal particle can be seen as an instance of the spine representation. But for the branching random walk, so this definition, or the definition that one uses normally, comes from Russell Lyons in his paper. A simple path to Biggin's martingale convergence for the branching random walk. So you get easily a PDF if you search for this in Google. So I think it was 97 or 95, between 95 and 97. Okay, so we won't get to the spline representation today, so which is the main point of this article, but at least I'm going to define the general branching random walk. So before we had a fixed tree, which was, for example, a binary tree, and we had attached a Gaussian variable to each edge. And now this tree will be a Gelton-Watson tree, and the displacements will not be Gaussian anymore. So we start with an ancestor at 0. Now, an individual at position x. So now an individual at position x spawns offspring in the following way. He throws points according to a point process, which is translated by x. Okay, so throws offspring according to a point, or according to a copy of a point process So that's denoted by script P and translated by X. And then all of its children are going to reproduce this independently. So each child repeats this process independently. So independently of the others and of the past. Independently of the others. Okay, I'll just draw a picture so that you can visualize it. So we start with one individual here at point 0, and so this will be a time. So the time we will always denote it by n. And so the next time interval we will have here, say, 3 particles thrown on the line according to some point process, and now each child does the same. Okay, so this one here, for example, has these 2 children. This one here has, for example, only 1, and this one here has no children, for example. So this is also possible. And then these ones here continue. All independently, and this one here also has no children. Okay, this is the general branching random walk. So now, of course, if you only look at the number of particles at each time, then this is just a Galton-Watson process. Okay? All right. Well, just in order to make the connection with what we did in the beginning. So now if we define the log Laplace transform, so now we define it by the expectation of, again, of an exponential, but overall the individuals of the first generation. So here, so this is the absolute value of the modulus of V is the generation of V. And this means that we take all the individuals in the first generation, and so we take the expectation over this sum here. And so we will always suppose that this is finite for all lambda, for simplicity. And furthermore, we will suppose that the derivative in 0 is 0, and again that the second derivative is strictly positive. Okay, so this means that the expectation here is 0. And then we can define again a rate function, Ix, which is the supremum over lambda x minus the log Laplace transform. And so now the law of large numbers can be seen, so for the branching random walk that Ofer showed today in the lecture, can be seen then as an extension of Cramer's theorem to branching random walks. And well, I will not write it down here. I will just recall now how we link this to the Gaussian case. So if we have say k independent Gaussian variables. So this point process here consists of k Gaussian variables which are independent. Then we simply have here, so this expectation is then k times the Laplace transform of a Gaussian variable. And so we will just have here the log Laplace transform of a Gaussian variable plus log k. Okay, and the rate function will then be x squared over 2 minus log k. So the rate function will be negative at some point here. So this one here is minus log k, and the position of the rightmost particle divided by n will then converge to this number here, so x star, which is exactly the point at which the rate function is 0. Okay, so the next time we're gonna reprove this result using the spine representation, which is a very useful tool to study branching random walks. So, of course, especially if you have here this general branching random walk, but it's also very useful if you have just a fixed tree and Gaussian variables. And so this will lead to another proof here of the law of large numbers. Thank you very much.